Okay, it's lesson 12. We are chugging through derivatives. We are plowing through finding all sorts of things out about derivatives. In this video, we'll take a look at derivatives of trig functions because polynomials are great. Polynomials are not all there are. So the standard trig function that we consider first is the sine function. The cosine function is similar, so we don't worry about the cosine function. We worry about the sine function. Cosine is derived similarly. If I can, we should take a moment. It appears that at this spot here, the derivative is 0. And it appears at this spot here, the derivative is 0. And similarly here, and similarly here. The derivatives are 0 at those places. At this spot here, it looks like the tangent comes in at about a 45-degree angle. That's where the slope is 1. Slope is 1 right about there. And also here. And also here. And at this spot, the slope looks like it's -1 coming in on a 45-degree angle the other way. So it looks like the derivative function does this. It looks like the derivative of the sine function looks like this. But haven't we seen this function before? Could it be that f prime of x is cosine x? Is that possible? And the answer is yes, that's possible. The theorem for us to consider is that the derivative of the sine function is in fact the cosine function. And to do that, we're going to go back to the definition of derivative. If we're looking for the derivative of the sine function, the derivative of the sine function is the sine at x plus h. Oh, no, it's not. I made the mistake I tell you not to make. Golly. It's the limit as h approaches 0 of the sine of x plus h minus the sine of x over h. This is the difference quotient. Function at x plus h, function at x over h, limit as h approaches 0. So then I have to dig deep into my memory bank and I have to figure out what the sine of the sum of two angles is. And there is a formula that does that for us, and you don't have to know it. It's fine if you don't. The sine of x plus h is sine x cosine h plus cosine x sine h. You don't have to know that. It's a trig formula. It's something that you used to be familiar with in high school. So I'm going to do two things at once. I'm going to break this up into two fractions, and I'm going to group these two things together. So over here on the left, I'm going to suck out a sine x, and then what's going to be left is going to be a cosine h minus a 1. That's all over h. And then over here, I'm going to have what's left. And what's left is this stuff. This is what's left. And that's cosine x times sine h over h. So I'm going to know what to do with this if I know what this limit is and I know what this limit is. Because as h goes to 0, sine x doesn't care, but this limit probably does. And cosine x doesn't care about h, but this limit probably does. So your author includes in your text the graphs of sine h over h and cosine h minus 1 over h, and they help us get an idea of what happens as h approaches 0. As h approaches 0, it appears that the limit here goes to 1, and as h approaches 0, it appears that the limit here goes to 0. And so if we use the graphs to help us to see the limits, then that's 0, that's 1, and the derivative of the sine function really is the cosine function. In a similar way, the derivative of the cosine function is negative sine x. We can go through a similar proof. It runs much the same way, and we end up with negative sine of x. So the derivative of the sine function is the cosine function. The derivative of the cosine function is the negative of the sine function. So what does that mean for us? Find f double prime if f of x is x cosine x. Well, that's not too bad because we're going to take two derivatives. This is a product, so the product rule is so much fun. It's 1 prime 2 plus 2 prime 1. And so for those of us who like to simplify, because we're going to do something with this, we can, and then we say, okay, well, let's do it again. Let's take the derivative of this, and that's not too bad. This is a product. The product rule is so much fun. It's the first times the derivative of the second plus the second times the derivative of the first. And then this thing gets its own derivative over here, and then we simplify like we're supposed to. That's okay. And then this is a minus sine x, and that's another sine x. So that's like that. And so that's f double prime. Of course, we can do this with quotient rule also. Quotient rule also is a legitimate thing. Find g prime of x if g of x is sine x over x squared plus 1. Well, again, that's doable. This here is a quotient, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. And surprisingly, this does not simplify. Can't cancel the x squared plus 1s because of that pesky minus sign. There is nothing that reduces here. We leave it in this form. That is often the case with quotients. This is an appropriate time for a couple of OYO questions, couple of things for you to figure on your own. One would be to find h prime of x if h of x was x over cosine x, and the other would be if you have some position function s of t, and that was the square root of 3 times t plus 2 cosine t for times between 0 and 2 pi. When is the particle at rest? So if this is the position function for some particle, if it gives us the position at any time, when is the particle at rest? And so it is worth thinking about what it means in calculus language if the particle is at rest. Those are things to think about. Of course, there are other trig functions, but they're just combinations of sines and cosines, so we're actually okay to derive them in standard ways. For example, the tangent function has a derivative, but tangent is just sine over cosine, and so we use the quotient rule exactly the way we envision. Denominator times derivative numerator minus numerator times derivative denominator over denominator squared. And you might think, well, we'll just leave it like this, but this is too good. This is cosine squared x plus sine squared x. And you know what cosine squared x plus sine squared x is. That's 1. And so sometimes you see the derivative written like this. I know the International Baccalaureate writes the derivative of tan x like this, but most often in American calculus textbooks, you see that the derivative of tangent x is secant squared x, because secant and cosine are reciprocals. In a similar way, the derivative of the cotan function is negative cosecant squared x. Also, the secant function has a derivative. It's smooth throughout its domain. You can draw a tangent line at any place in its domain. We're looking to take the derivative of 1 over cosine x, and we do that in the way you would envision. We use the quotient rule. Denominator times derivative numerator minus numerator times derivative denominator over denominator squared. That's a little bit harder to see. The numerator is sine x. It's actually 1 times sine x, because that negative 1 and that negative 1 multiply to a positive 1. The denominator is cosine x times cosine x. And so the way this is usually written in calculus textbooks, 1 over cosine x is secant x, and sine x over cosine x, that's tan x. And so the derivative of the secant function is secant x tan x. In a similar way, the derivative of the cosecant function is negative cosecant x. Oh, that's a cotan. So sorry. Cotangent x. So one more example. Find an equation of the tangent to y equals tan x at x equals pi over 4. That's this function. Got your asymptote at pi over 2, got your asymptote at negative pi over 2. Pi over 4 is right about there. There's your tangent line, looking for an equation of that tangent line. It is worth noting that at pi over 4, the y value is the tangent of pi over 4, and that happens to be 1. Now to find the slope of the tangent line. The slope of the tangent line is the derivative of this function. Well, that was secant squared x evaluated at pi over 4. Well, what's that? Well, the secant of pi over 4, that's the reciprocal of the cosine of pi over 4. 1 over root 2 is the cosine of pi over 4. So we take that reciprocal and square it, and that turns out to be 2. So then we write the equation of a line. I know how to write the equation of a line. It's y minus y1 equals x minus x1 multiplied by the slope. And you put it in a box. And you're done. There are some things you should know how to do before we gather. You should know how to write the equation of the tangent, an equation of the tangent, to y equals x cubed plus cosine x at the point 0, 0. That's not even on the function. What am I doing? 0, 0 is not even on the function. 0, 1 is on the function. 0 cubed plus cosine of 0 is 1. That's on the function. So that's something to consider. And then the other question for you to consider would be to find dy dx if y is 1 plus secant x over 1 plus tangent x. That's a nice quotient rule question. And then if you're one of those people that's thinking, I want all sorts of practice situations, well, then I would encourage you to do the questions that are listed here in green. They are all out of the OpenStax book, Strang's book, available freely online. Our 15 minutes are up. Thanks for sticking with us. We'll see you in class.